Hello and welcome. This is Bhaskar Napte from Pharma Growth Hub. So, as a part of this video, we will try to understand how one can develop a method for a chiral compounds using protein-based chiral column. So, let us first understand what is meant by protein-based chiral column and what the stationary phase contain. So, the protein-based chiral column, the CSP stands for chiral stationary phase, is made up of proteins having chiral amino acids because the proteins has the chiral amino acids because of asymmetric carbon atoms as well as the glycoproteins which are also having the chiral amino acids and the sugars. So just to let you know how this amino acids looks like, here is an example of serum albumin. So don't get scared by looking at the structure. It is quite scary, but let us not worry about that. So these proteins are covalently bonded with the wide pore silica or sometimes the polymeric support. So you saw the protein structure in the last slide. So that kind of protein structure is bonded covalently with the wide pore silica. So you can imagine that there is a silica support and then there is a protein molecule and this forms the chiral stationary phase. So protein columns are compatible with aqueous buffered mobile phase. So if they are compatible with aqueous means water plus buffers, why don't this column can be used for reverse phase mode? And that's the great advantage of the protein columns. The protein columns can be used in the RPLC. You can see there are many applications of the protein columns in biological products analysis, but it has some lesser applications when it comes to preparative applications because of the less sample capacity. Otherwise, the protein-based columns are the best one. And here are some manufacturers of the protein columns like you can see on the screen. And there can be many more. I just thought of bringing some of them on the presentation for your understanding. So what kind of proteins are used for chiral stationary phase? We talked about serum albumin at the very beginning of this presentation, but these are some of the proteins. So albumins are very popular. The albumin like bovine serum albumin or human serum albumin are used to manufacture the protein-based columns. Glycoproteins are also popular like alpha acid glycoprotein, ovomucoid, or no ovoglycoprotein, avidin, riboflavin binding protein. They are very popular stationary phases. Enzymes like trypsin or lysozyme or pepsin, they are also used widely. And there are some more proteins which can also be used to manufacture the protein-based CSPs. So it is very important to understand some of the important characteristics of the protein stationary phases. And here are some popular stationary phases like BSA, HSA, AGP, OVM, CGP, CG, CBH, Pepsi. The description is given on the screen. Go through that. Molecular weight is important point. But I think isoelectric point is very important. And we will talk about the isoelectric point in the next slide. So how the isoelectric point helps you in deciding the usage of the protein-based chiral stationary phase. So let us talk about the isoelectric point definition. So as the definition, a pH at which the net charge of a protein molecule is zero. You know that the protein consists of acidic substituent and the alkaline functional groups. Acidic functional groups like COOH, right? Carboxylic, and then there can be a nitrogen-based alkaline functional groups. So the acidic functional groups may carry a negative charge in their ionization form. Similarly, the alkaline functional groups can takes the positive charge if they get protonated. So there are chances that the protein molecule can be having negative and positive charge. But there comes a pH, the pH at which the net charge is equal to zero. I mean, there could be a positive charge, there could be a negative charge, but they will be of the equal magnitude. And because of that, the overall charge or the net charge of the protein molecule becomes 0. And that particular pH, because pH defines the ionization, isn't it? The pH actually defines the ionization of acidic group and the alkaline group. So there comes a pH where these acidic and alkaline molecules may undergo ionization, but they will have a similar magnitude of charge, and because of that, the negative charge, you know that it will again nullify the positive charge, and hence the entire charge of the molecule looks like a zero, or the net charge on the molecule looks like a zero. So that particular pH is called as isoelectric point. It is very important. If you do not understand this, you may not understand the functioning of the protein-based CSPs. On either side of the pi, the protein can have either a net positive or net negative charge. Understand this. So there comes a point, let us say the pi, that stands for isoelectric point, for the given protein is, let us say, 4. The 4 is the pi. So what is the net charge at the pH equal to 4? 0, right? But the moment the pH becomes 3, then, so what is going to happen? The moment the pH goes to 1, now the acidic charge will not undergo ionization, isn't it? But can you see that the alkaline molecules or the functional groups may undergo protonated now? May undergo protonation, and that can develop the positive charge. So below pi, the molecule have the positive charge, and what is going to happen the above pi? On the alkaline side, for example, the acidic functional groups may undergo ionization, result into a negative charge. So at higher pH, the net charge on the molecule can be a negative. Now, this charge conversion is certainly going to help a lot in understanding the retention mechanism of the compounds. So please remember this very important information. And that's what I try to connect now. Mechanism of interaction on protein-based stationary phase. See, everything relies on to the very principles of retention and onto the protein-based molecule. Now, these are the two important mechanisms because of which your compound can undergo a retention. So, the ion exchange is the first one or the primary one, and the hydrophobic interaction is the secondary one, but it also plays a very important role. Let us now first talk our discussion with the ion exchange interaction. How this ion exchange interaction happens. So opposite charge on solute and stationary phase brings ion exchange retention possible. Unless and until your protein means what? Stationary phase, because you are talking about the protein based stationary phase, isn't it? So unless and until your protein and the solute means your analyte, has opposite charge. For example, if your protein has a net positive charge, and if your analyte has a negative charge, then they can say to have a opposite charges, and during that time the ion exchange is possible. And I hope you remember that at what pH the protein molecule can have the net positive charge, and at what pH the protein molecule can have the net negative charge. It totally dependent on to the isoelectric point of the protein. If you don't remember, please go back again, watch that portion of this video and then come forward. The protein stationary phase assumes a charge either above or below the pi of the protein. I talked about that, above or below of the protein, a pi, how this protein can have a net negative or net positive charge. Now I need your complete attention for this point of discussion. An increase in the pH of the mobile phase increases the negative charge. Why? Because the pH increases means what? It may go towards the alkaline side. So if the pH goes to alkaline side, can you see that there is a chance of ionization of acidic functional groups? Right? It can donate the proton and develop the negative charge. And as an example, like COOH is present onto the amino acids, means the protein, right? So that COOH, so carboxylic functional groups can lose the proton and yields a COO minus, that is a negative charge. So by increase in the pH, the protein-based stationary phase can develop a negative charge, and you understand because of what the negative charge gets developed? Because of ionization of the acidic functional groups. As an example, ionization of carboxylic functional groups. And when this happens, then there is a decrease in the retention of acidic compounds found. Now, what is the ionization state of the acidic compound? I assume that the acidic compound undergoes ionization. Look at here. We are now trying to determine the retention in the mode of ion exchange. So when the ion exchange mode will function and work, if and only if there is a charge present onto your analyte and the mobile phase. So big if it's an acidic compound, what is the expected charge? If it is acidic compound, if it undergoes ionization, what kind of charge that compound will develop? Tell me, positive or negative? Because it can lose the proton, and out of that it can have the minus charge. So I say if X is my acid compound, X minus will be the charge present. Let us now analyze the situation one more time. Our stationary phase has a negative charge. Our analyte will also have the negative charge. I would like you to read the first statement now. What is the statement? The opposite charge on solute and analyte on and stationary phase brings ion exchange retention. Tell me in the chat box whether it is possible to have this ion exchange retention possible in the very first case. Negative charge onto the column and negative charge again onto the analyte, the same charges. So it is not going to bring any kind of ion exchange possible, and because of that decrease. So this kind of acidic compound will have the reduced retention time possible. I hope you understand this. Similarly, let us understand the second important statement. An increase in the pH. Again, I am taking the same situation where because of the increase in the pH means pH may go towards alkaline side, and because of that you can see the ionization of the acidic functional groups happening onto the column. The column is protein-based column containing acidic plus basic functional groups. So towards the alkaline side, which functional groups will undergo ionization? Acidic or basic? Certainly acidic, right? So these acidic functional groups may undergo ionization, and that they will result into a negative charge like COO minus. And in case if you have the alkaline compound, so the alkaline compound in its ionization form, in its protonated form, will have which kind of charge? Will have the plus charge. So if X is the basic compound, it can have X plus. It can have the X plus as a charge. And now just compare the charges now. Are they similar or opposite? I mean, compare the charges between your stationary phase and the compound, and you will find that they are opposite to each other, and because of that the ion exchange retention is possible, and that's the reason the retention time for the basic compound will get increased, will be higher as compared to the acidic compound. Let us talk about the decrease in pH situation now. In case if you decrease the pH of the mobile phase, now tell me which functional groups will undergo ionization in the lower pH, in the decreased pH, because your stationary phase is what? Is a protein based stationary phase, and protein has two functional groups, you know that one is acidic and another one is basic. So in the acidic side, lower pH, can the acidic functional groups undergo ionization? Certainly not. So which functional groups then will undergo ionization in the acidic pH? That is the basic functional groups. The basic functional groups can get protonated and develop the positive charge. And that's the reason I said over here that the decrease in the pH will increase the positive charge, because of maybe the protonation of the N terminus. And let us say you have acidic compound now. So as a thumb rule, we said that the analyte will always be into a ionization state. So in case if it is acid, what kind of charge it will carry in its ionization state? X minus. So look at the charge now. The stationary phase has a positive charge and analyte has a negative charge. Are they opposite to each other? Certainly yes. And because of that, the great ion exchange retention is possible. And hence I said that there will be increase in the retention time of acidic compound. Similarly, let us take an example of the basic compound. Decrease in the pH. Decrease in the pH will increase the positive charge. We discussed this point. And in case if you have the basic compound now, tell me in the acidic pH, will the basic compound undergo ionization? Yes or no? Certainly yes. And that can have the protonation happen and it will have the X plus now. Now let us compare the charges present onto the stationary phase and the compound. Positive charge on the stationary phase, positive charge of the analyte, are they opposite or similar? They are opposite. No, they are not opposite in the last case now, but they are similar, and hence because of that the ion exchange mechanism is not possible, and that's the reason I said over here the decrease in the retention time for basic compound. The basic compound will retain for the shorter amount of time. I hope you understand how this ion exchange mechanisms takes place in case of protein-based chiral stationary phase. It's a very important point. The second mechanism by which the retention is possible is what? The hydrophobic interaction. Hydrophobic interaction, and the hydrophobic interaction is what? When there is a no charge present either on the stationary phase or there is no charge either present onto the analyte. Hydrophobic means non-polar interaction. So an increase in the pH tends to decrease the retention time of acidic compound. Why? Because if the pH gets increased and if the compound is acidic, will that acidic compound undergo ionization at the higher pH? Maybe alkaline pH? Yes or no? It will undergo ionization. So, will this acidic compound now a non-polar or polar? Understand that any compound in its ionization state is the polar compound, right? And any compound in its non-ionization state is the non-polar compound. So, but if the acidic compound undergoes ionization in the first case, we can say that it is a polar compound. Assume that our stationary phase is a neutral one. It's a non-polar at exactly at the isoelectric point pH, right? In that case, will this polarized acidic compound have the interaction with the neutral stationary phase? Certainly not. And because of that, we say that the retention time for acidic compound will be low in the higher pH because of the weaker hydrophobic interaction. The second example, increase in the pH, but now you have the basic compound. So will the basic compound undergoes ionization in the higher pH, means on the alkaline pH? Certainly not. And hence it will remains as a non-polar because it is non-ionized compound, so it is a non-polar compound. So your stationary phase is hydrophobic, your compound is non-polar or hydrophobic, so hydrophobic interaction is very strong, and because of that at higher pH the alkaline compound retains for the longer time. I hope you understand the difference between the retention of acidic and basic compound. Similarly, a decrease in pH now, what is going to happen to the ionization of acidic compound? Will the acidic compound undergoes ionization in the acidic pH? No, they will not most of the times, and hence they remains hydrophobic or non-polar. So whether there will be great hydrophobic interaction possible now? Certainly yes. So at the lower pH, acidic compound will have the increased retention time. And the last but not the least, a decrease in pH tends to decrease the retention time of basic compound. I hope you will be able to analyze yourself and tell me the answer in a chat box. Let us talk about the important point of the method development, and that is the organic modifier or the organic solvent. Because in case of your HPLC, you may use different organic solvent, and in case of the chiral separation, When you are using the protein-based molecules, can you use the reverse phase mode of your HPLC? Certainly, yes. I think we talked about this point at the beginning of our presentation. So, increased organic modified concentration weakens the solute protein hydrophobic interaction and reduces the retention time. I hope you understand this concept. Higher is the content of organic phase, right? We call that organic phase is very strong organic phase, and because of that the retention time of your compound gets reduces. Hmm? And the lower is the content of organic solvent in the mobile phase, the retention time of the solute gets increased. Here are some examples of the organic modifiers. 1 or 2 propanol and acetonitrile, ACN stands for acetonitrile, are commonly used as an organic modifier in the protein-based CSP analysis. And diols like ethylene glycol and 1,2-butanediol are used to change the retention and selectivity. So these are some of the examples. Let us talk about the very specific columns like OVM and AGP comprise a wider range of organic solvent types and concentrations as compared to the protein CSPs. Let us talk about the selection of the pH, and I hope you realize the importance of the pH in case of protein based columns, because they actually determine the net charge onto the column. So whether the ion exchange is possible or hydrophobic interaction is possible is dependent onto the pH of the mobile phase and the pi means isoelectric point of the stationary phase. So pH affects solute retention as an effect of either hydrophobic interaction or the ion exchange interaction. And we talked on these 2 points in some of the few last slides. Solute retention increases when the charge on solute and column are opposite and maximum. Right? We discuss about that. Positive, negative will have the interaction, right? So that is called as ion exchange interaction. Acid racemates are more separated on basic columns. I repeat the statement one more time. Acidic racemates are more separated on basic columns due to the possibility of opposite charges on solute and column, right? Because of the ion exchange possibility. In case if you do not understand this, the formation of the charges, please go back to the same video and understand the ion exchange mechanism one more time. The basic racemates are more separated on acidic columns due to the possibility of opposite charges on solute and column and the great chances of ion exchange possibility. And here are some examples I have given, like pepsin and AZP for the which are acidic columns, and BSA and HAS are the basic columns. OVM and CBH have intermediate pi and can be used to separate acidic and basic mixture. Solute retention increases when there is no charge on solute and the protein where there is a hydrophobic interaction dominates, right? So when the hydrophobic interaction can dominate, tell me, when there is no net charge onto the protein and when your compound is also non-ionized, hydrophobic interaction. Let us talk about the selection of ionic strength now, because you are going to use buffers to maintain the pH to your mobile phase, and the ionic strength also needs to be looked in. So ionic strength has a smaller effect on selectivity and retention. Not much role, but increase in salt concentration decreases the retention, maybe because of the common ion effect. So understand this. When the charge on solute and stationary phase are opposite, ion exchange retention occurs. Do you remember this? I hope yes. And an increase in salt concentration will decrease the retention. So in case of ion exchange phenomenon, the higher salt concentration can damage your resolution and the retention time. Hydrophobic interactive effects tend to increase retention at higher salt concentration, especially for neutral solutes. So this is the way I think you can understand what information you must gather about your molecule, about your column, and what precautions you must take, how you can select your column based on to the analytes chemistry, how one can select pH, how one can select the organic modifier, and even how you can think about the concentration of your buffer salt. Thank you so much.